Hi guys, welcome to our channel of Sciences and Mathematics. Our topic for discussion today is going to be a proof of the cosine rule that we have already mentioned in one of our videos. And we have already mentioned that this cosine rule is used to find maybe angles between different parts of a triangle, and also the sides of a triangle, of course, which consists of these unknown angles. So in this case for today, it's going to be using the concept of maybe Pythagoras theorem and the others that we have learned, and trying to see whether the cosine rule holds or not. So this is going to be very much applicable in some of the areas that we're going to find. And in us defining or maybe trying to confirm that the cosine rule holds is going to assist us, of course, in expounding on other similar rules that we're going to use, like the sine rule, etc. So for that case, thank you and welcome. So as I've said, today we're going to use an illustration and try to find out whether the cosine rule that we have discussed in one of our videos is basically applicable, or maybe it holds or not. So I'm going to use that use an illustration for our case here of that specific two sets of a triangle, so matched together. So in this case, I'm going to give this point Q, R, and then P. So as I said about the concept of angles, whenever I'm going to measure angle Q, this is going to imply angle RQP or PQR. So basically, whenever I'm talking about an angle PQ, angle R is going to represent this, angle P is going to represent this, angle Q. Whenever I mention about RQ, then it's going to imply the distance between those two specific points. But I'm going to use the lowercase letters in order to represent the distances for P. So this is opposite, small p, opposite that one, R for that, and then Q for the distance between this one and this one. And then I'm going to give this specific point as point S, which is perpendicular to RP at that specific point, and the distance between Q and S is going to be H. So this is going to form a right triangle system, and we're going to apply the concept of Pythagoras theorem in trying to find out how we can be able to represent those specific sides. So therefore, in this case, if we have triangle, this triangle QRP, we can define the cosine of the function R using this specific. We said that we can use this acronym in trying to define the trigonometric function. So therefore, we can be able to define the cosine of R by using, this is the cosine of angle R that is. So I said whenever I talk about angle R, I'm going to imply this one. The cosine of R is going to be adjacent over the hypotenuse, which is going to be the distance between, so this is going to be RS over the hypotenuse, which is represented by small p. So therefore, this is how we're going to define the cosine of R. So therefore, this is going to give us the concept that the distance RS can be given as small p, the cosine of R. So RS can be given as p, the cosine of R. So if we try to compare this one with the distance Q, we have found the distance RS. So in trying to compare the distance with the distance Q, we can be able to define the distance SP using this particular concept. So if this one is P, the cosine of R, so therefore Q minus the cosine of R is going to give us SP. So therefore we can define SP as Q minus the cosine of R. So that is from the comparison between the two. We can just define this one as our first equation for that case. We're going to use it for comparison somewhere. So in the triangle QRS, this is the right triangle. So according to the sine we can be able to define the sine of angle R still. So in triangle QRS, the sine of angle R, which is sine R, can be represented as opposite over the hypotenuse, which is going to be SQ over P. So therefore, we can be able to represent SQ as P, the sine of R. So that is going to give us equation 2. And in that case, in the triangle QSR, we can apply Pythagoras theorem in order to find R. So how can we be able to define R in this case? So from Pythagorean identity or Pythagorean theorem, we can be able to define this one by finding R squared as SQ squared plus SP squared. But remember, from this we have already defined what SQ is and what SP represents. So we can be able to write this R squared in terms of those two specific definitions we have given for SQ and SR as this is going to be, okay, just a minute. This is going to be P sine of R, P the sine of R, this has been squared, plus SP, small q, minus just a minute. So this specific definition was P the cosine of R. So therefore we're going to have P cosine of R squared. So therefore from that one we can be able to still expand that particular formula. And we are going to see that this is going to give us I think I just do away with this so that we have a continuation of that one from here. So we're going to have this R squared represented as P squared, the sine of R squared, this one, this is a square of this specific term, plus, now from algebra when we have A minus B or A minus this B squared, then it's going to give us a general formula for Q squared minus 2QP the cosine of R plus P squared the cosine squared of R. It's just a continuation of this, or maybe I can just squeeze it here for the sake of just trying to find some clarity. So this is going to be P squared the cosine squared of R. Just try to minimize on that space. So I'm going to do a rearrangement of this specific formula and try to put some of the terms together, whereby we will have the P squared, the sine squared R plus P squared, the cosine squared of R, and then minus or plus Q squared minus 2QP, the cosine of R. So if we try to look at this specific formula, we can be able to factor out this concept of this is Q. we can be able to factor out this concept of this particular set of b squared, and then we have the sine of squared r plus cosine squared r plus q squared minus 2qb, the cosine of r. This is an identity from trigonometric identities. We're going to see that this is going to represent 1. So therefore, I'm going to do away with this part so that we can be able to just use it. So in this case, I'm going to just expand on this formula still, and then I find that it's p squared plus q squared minus 2pq, the cosine of r. So this one represents r squared. Now this formula is analogous to the one that we had discussed, of course, which is our cosine rule. Now suppose I have r here represented, suppose r represents c, p represents a. I'm just going to give an illustration so that maybe we can be able to connect and relate on this. So suppose p represents, this is a. I'm going to give it in terms of a, b, c, and this q represents b. Angle r is represented as angle theta. So suppose this is the case, then we're going to represent this formula as r. So c squared is equals, p is represented by a squared plus q is represented by a, for p squared minus 2ab, the cosine r, which is angle theta. So this specific formula is what we call the cosine rule. And if using this set of triangles, we can be able to illustrate that the cosine rule is basically applicable. I've just used this specific example because it's the one that we normally mention, or the one that is normally applied in several cases, in that it's analogous to the specific equation that we have derived from this set of triangles. So basically, that's how we can be able to show that the cosine rule using the concept of vectors is applicable. And of course, we can be able to apply it in trying to find out solutions to some of the problems that we may encounter so far as triangles are concerned. Now, I'm going to use one specific example to try and show on how we can be able to use this specific cosine rule. So I'm going to do away with that. So suppose we have a triangle which is like that. This is for A, B, and C, and therefore this is B, A, and C. And the length for this specific sides is 26 centimeters, 37 centimeters, and then 42 centimeters. So we have talked about the relationship between angles and the sides of a triangle of this particular case. And therefore, we're going to use the cosine rule that we have already illustrated in order to find the angle, maybe angle theta of this specific example. So therefore, from the formula, the cosine rule states that, so I could have given identities for these different sides, but we can just illustrate as n of the side arbitrarily, the A, B, C, or C can be represented by b squared plus c squared minus 2bc, the cosine of theta or angle A. So by doing a substitution, we're going to see that A squared 37 squared is equals b squared 26 squared plus c squared 42 squared minus 2 into A into B 26 into C is 42, and then the cosine of theta. So basically, whatever that we have not been provided with in this case is the cosine of theta. Therefore, we're going to make the cosine of theta the subject of our formula. The cosine of theta will be given as 26 squared plus, this is 26 squared plus 42 squared, and then minus 37 squared over 2 into 26, and then 42. Just trying to confirm whether I'm writing the correct figures. So this is going to be 1071 divided by 2184, which is going to give us 0.4904. So the cosine of theta is equals to 0.4904. We can find theta by finding the cosine inverse of theta, which is going to be 60.63 degrees, maybe to 2 decimal places. So in this case, this is how we can be able to apply the cosine rule in trying to find out unknown angles of that specific triangle. So I hope that we have been able to follow the procedure for trying to prove that the cosine rule, of course, is applicable. And the example that we have given, of course, is going to show us that using the cosine rule, it will be easier for us to try and find out angles and sides of unknown sides of a triangle, as we have illustrated in our last example. So for that case, that is it for today. Bye guys, God bless.